so I can start, and sorry for this circumstances. I arrived just in time, and I need more time to prepare because of some reason. For example, because I record the presentation, and also if I write something on the table. I will need information from you because I started working here. I have been started working here on 1st of October, so someone else gave the lectures and the practice. And I got some information, but it's not satisfactory. But we will see. So here is the presentation of the lecture. Yes, this is full screen. Yeah, just the what is it? Okay, so my name is Gábor Facskó. I am a space physicist, and I will give you this lecture and presentation, and also okay, I hope it's visible, so it's too high to climb there. So I will give you the this presentation and this lecture. I started work here 1st of October, as I mentioned. I'm assistant professor here. It's the lowest rank that you can get with PhD. I'm a space plasma physicist, and I also work in the Wigner Research Center for Physics. Then I'm senior research fellow. That's equivalent to the docent, the associate professor rank. During the year, I will do the habilitation, and I will have higher rank and more salary, but well, that's one thing. This is my email address, and only my email address is working right now. I kindly ask you to send me emails today or in the next week, because I haven't had my network access, so I cannot send you messages. I have the list. I'm very happy because you are foreigners, Hungarians, and you are 37. That's very nice number, actually. And last year I taught more than 200 people. I have some very strange behavior. One, I record this presentation and also my drawings and everything. And the other, that's very weird, I answer emails. I don't know what is the situation here at this university, but at my previous workplaces, the teachers, the professors neglected the emails. Actually, at my previous place, even the colleagues neglected my emails too, and that made some communication problem. I'm originally a physicist, and I graduated at the Obuda University in 2000. And now there are BSc in physics, the MSc in teaching, and so on. I was trained to researcher. And because I did this because I wanted to be astronomer. In that time, there was no MSc in astronomy. It was quite difficult. You had to learn physics, geophysics, meteorology to become an astronomer. Later, I also learned computer science, and I have a BSc, but not that BSc that nowadays has. It was in 2004. And now, as I told you, I'm working at this university. Honestly, I'm not 100% sure where I'm working. I know the faculty. It's Kandokánon Faculty of Electrical Engineering. That's great, but there are institutes, and it's not clear in which institute I am. Doesn't matter, I will know it. But I'm sure I'm work also in part-time in this Wigner Research Center for Physics. Do you know what is KFKI Central Institute for Physics? Have you been at that place? Have you been at Chilebets, at Normafa? Normafa. Okay, if you take a bus to the end of the road which starts at Normafa, then you will find yourself a place where there is a nice stable, tennis field, also some buildings, and on the other side there's a locked area. It's the former campus of the Central Institute of Physics. There computers were made, and nowadays we have a nuclear reactor. There are 3 places where you can find nuclear reactors in Hungary. First, everyone knows Paks, where there is a nuclear power plant with 4 reactors. The second is nearby, at the shore of the Danube, at the Technical University of Budapest, and we have the fixed. Its power is something 10 megawatts, and 8 days it works, 8 days it does not work. I will tell you something that useful, which is related to the activity there. 8 days working, 8 days do not working means the researchers 8 days are alive and awake, and then 8 days they sleep, or something like this, because they use this reactor for material studies, material state physics, and some diagnostic. And also they need a lot of isotopes. It's very good for cancer treatment. It's very good for some other things like portable X-ray examination or something like this. Okay, as I told you, I have a homepage. Actually, I have 2, but use this homepage right now. I will have info page and everything here at this university, but I don't know how. I don't know anything. Last Thursday I was here and checked this room, but I didn't check the light, but I just checked the projector and other things. And this is what I know right now. I analyze spacecraft data. I also do simulation, good afternoon, and a lot of other things. I did my PhD at the ELTE, at the Electrical Engineer University. Then I worked in France, in Orléans. It's not New Orleans, it's 150 kilometers so far from Paris. I did some instrumentation and I picked up a lot of engineering stuff. And I worked in the EMOT at Enlightos, the Finnish Meteorological Institute in Helsinki. Then I started my magneto hydrodynamic simulation. That's some magnetized fluids means this MHD. And then I returned to Hungary for a while. It was great, but it was so successful that I moved to the European Space Agency. I hope many of you will work there, and now I work this Wigner. But because of some reason, I started to work at the Milton Friedman University in Budapest. It's in it's northwest part of Budapest. It's very close to the other campus at the Bécsi út, Bécsi Street. I had some problem. My family is in Pécs, where I live right now. I will go and I will come. I travel every morning before your lectures from Pécs, and I will return there. I hope next time the train will not be delayed by 25 minutes, but it could be 40 minutes, 1 hour, whatever you want. I worked also at University of Pécs. And at the Milton University, I taught IT students for informatics, like Linux, Unix, C#. This is also Unix, LaTeX. I taught mathematics in Pécs, And now I am here, and this is the first time when I'm standing before university students and I teach physics. Actually, I have many private students, pupils, students, and I always taught them informatics and mathematics, not physics. There are two exceptions, so it's a very special occasion. I'm very happy. I hope you will enjoy my talk. Until end of the last month, I worked as external contractor for the NASA Goddard Space Flight Center. That's it. I had already, I was supervisor of one MSc student, and now I'm supervisor of another. And I had 3 BSc IT students and 1 TDK students. And I have a very special student. I worked abroad, and I have a lot of things. I always say sounds coming out from my mouth, and no one listens to me. He was the only one who listened to me. He is not the richest guy from this country or this city, and he asked me where he could find a PhD position. So I provided him a list with 50 friends, and finally he was admitted to the University of Oulu. Oulu is at the northern peak of the Bay of Bothnia, very close to Sweden, in Finland. It has a sandy beach, very nice, it's unique in Finland. Just the snow melts in June, and now it have failed. Doesn't matter, it's very nice. I encourage him to restart the Hungarian national team of ice swimming, because during the winter they have places where the Finns build in icy river. Doesn't matter, not important. Okay, you are also special because you are in your first year, second year. Sorry, everyone else was in the first year. So you know very well what lecture means, what practice means, what midterm exam means, and what is signature. Don't you? So you know that if you don't have signature, that's hatching. So it's over. Because I had to explain this. Okay. Do you know what is TDK Scientific Students Conference? Not yet. Really? Okay. You are Hungarian? Okay. But you never heard TDK? Okay, speak English please, because the others will not understand us. Okay. If you want, I can give you topics and I can explain what is it. If you do some research, then you can get some preference and advances in admission for MSc. Also, you don't need to write a BSc thesis, or just sometimes you do not need to defend it. If you are bored because this your studies are too weak and you have many time, then I encourage you to do it. And my master plan is that you are electrical engineers. That's great. In space research, I mean in space industry, so there is something. There is astronomy. I'm not astronomer. I have an MSc in astronomy, but I am not astronomer. There is space research and there is space industry. It's a quite common thing. As in the European Space Agency, India, China, NASA, you can work as engineers to the space industry. There is a special thing that BSc, then you can start a PhD, or you can go to BME or anywhere else, and you could be aerospace engineers, and you can be a very special. So you can be the operator, you can be who plan the missions, you can build spacecrafts. Here, right now, from September, there is a group moved from the ELTE. They have built CubeSat and PocketSats. CubeSats are very small spheroids. It's a cube, 10 centimeters, 10 centimeters, 10 centimeters, and students build them, like you. The persons who work in the European Space Agency are like you. There are many ladies, but I have a very bad comment about this. They are a very common person. And around, for example, European Space Agency, there are companies. The European Space Agency has only 2,000 employees, and 20 or 25,000 works for a company, and they are borrowed to the European Space Agency. The members, the staff members of the European Space Agency must be European citizen, actually not European citizen, member state of the European Space Agency. But for this company, you can come any part of the world, from Pakistan, from I don't know, China, from Africa, whatever you want. It doesn't matter. The only thing is that you have to try. They like immigrants, they like ladies, really like ladies, and there are ways to go there. There are training. You can go find a training here in Hungary. You can apply for a training place for the European Space Agency or for a company which has a contract with the European Space Agency. It is paid. It's in France they call it stage. In Hungary usually it's not paid, sometimes not, but it's paid. It's not very big stuff, but you can pay your room and you travel, and that's it. And then you are there, you can apply for another training, or you can be a younger day trainee or something like this. So there are ways. I can explain you, not here, but if you have some organization, student, I can share this information. Okay, I talked about BSc technical topics, thorough advice, that was it. And there are some soft trainings. Apologize, I have no access to Teams, I have no access to Moodle, not yet. So I don't know how I will share these things, but I will always prepare the slides and I will share with you. Okay, here is the introduction, and let's start the conversation. So course objectives. Blah, 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 blah. Physics is interesting, very nice, it's fancy. There are many experiments that, and many features that you can use in your web. That's it. Okay, so I don't know what's this. I didn't, I copied and pasted everything. This is the topic, and now I need input. The Jolt? Silab. So I haven't seen him, just we actually once email. Told me last year he taught you this motion of charged particles and electromagnetic fields. So now I can start with the photoelectric effect and thermal radiation and the dual nature of the light. That's very nice. Okay, I prepared for this. Just so these are the topics. Have you learned this Bohr model, quantum numbers and everything? This year, in the last, okay, when did the lecture start? 8th of September? 8th of September. You was here 8th of September, first day, you were eminent, and there was a lecture. What is the topic of that lecture? Okay, thank you. I look at you because usually the girls has a much nicer handwriting actually it's not always true. Okay, so this is a big particle. You are okay. Oops. Wow. You are very good in linear algebra, and but this is not what Fourier force. Fourier force is not quantum mechanics. Reference frame. Okay, so this you start with the special relativity theory. Okay, so the quantum mechanics, and then there are operators. Also, you learned about how to the operators create. Then Heisenberg. That's okay. Okay. Thank you. This is okay. So I'm a bit lost. You definitely learn this reference frames, something. Then you learn these elements of quantum mechanics, Heisenberg's uncertainty principle, and Schrödinger equation. You know Schrödinger equation? You know, that was last time.
Not all of them, it was at the start of the, it was at the start of the first lesson, we learned about the Schrödinger and Heisenberg.
Okay, sure. So you have the Schrödinger equation.
Yes, we just learned about the theory part, but in classical and about the quantum mechanics.
So, this is a way of cheating actually. If you have, that's some extra credits. No, I'm kidding. Did you see this written? Oh, I forgot something, a very important thing. I think it is not in my slides. The requirements. It's a bit. That's the next one. Okay, great. So you had Schrödinger equation. That's great. Did you solve, for example, the hydrogen atom? Really? You really had these spherical functions, and you as the S, E, D, F electron flow. He did it at the board. Really? Show me. I need a half day to calculate it when I was a student. Thank you. Oh, there are very nice things, but don't see, but I see this Harmonic oscillator, it's enough. Okay. Have you ever heard about this Bohr model, Rutherford model, and everything? I think I saw it. So you learn this. Okay, so then I know where we are. It's fine. So it's photoelectric Everton thermal radiation. That's the topic. And then I will continue from this. Great. Thank you. Not easy to catch up. Okay, there are a long list of requirements. First, you should present here. Well, I highly recommend you to come, but well, I don't want to check you, so if you don't come, you fail, that's your business. You paid a lot of money, I guess, to come here. There will be homeworks, and I know you already had one homework. I don't know what is it, because I have no access to Neptune and Moodle. What is the homework? You haven't had the homework?
No.
Okay, you will have 3 homeworks, 5, and you have to do it in time, in specified format. It's free, and then you got some points, and then you will be pass. And you can get extra points if you do all of them more than 3, then you got 10% or 10 points or something like this. You have to write midterm exams. I called them tests. In Hungarian it's Zárthely, ZH. In the old days it means closed place test, because in the old age they locked the door. I will not lock the door, so no problem. Okay, this is for the signature. Yes, extra credit I explained you, and you have to write both tests for sufficient or pass. It's more than half points, it's higher than it was, and then you will get a grade. Okay, there is something which is recommended, this Richard Feynman book. Feynman is something American and very good. I learned from the Landau series. It's this one, and that was the minimum exam for a scientist if he wanted to work with Landau. He was a very good Soviet scientist. He was in his 3rd year when he was 16 years old. So he was very good. Unfortunately, he liked cars, fast cars, and he died in a car accident. But he has a lot of very good things that he had done during his life. Okay, so I talked too much. We have, how much time we have? So it should have started 40 minutes ago, and I have now 50 minutes to talk. Doesn't matter. So, thermal radiation. You know, there is this science thing. Just one other question that I would like to know. So, are you, who is foreigner, are you with the Stipendium Hungaricum? No? Erasmus. Erasmus from
the Kazakhstan. I think I guess the whole class.
Oh, so you are from Kazakhstan? So you just have this lecture with me?
It's the first time of lecture.
Okay, great. Then you know London, I guess. That is your professors, you know London. You are electrical engineers too?
Yes.
Don't you? Okay. Do you know Kronstein? Kronstein? It's a mathematical pocket book. I will show you. Actually, I will need more help during the practice because I don't know what I can expect from you, actually. These Hermian operators were very clear to everyone, for example. Really? So you like complex matrices and everything. Okay, the others, they are from where? So stipendium. Great. And there are Hungarians. So why do the Hungarians listen this talk in English?
Because it's more fun.
It's more fun. Great. Okay. You will learn my excellent accent. That's sarcastic. Okay. So let's start the real talk. Thermal radiations, black body. You know there is this science. This science is, well, 99% is useless. You cannot do anything with it. It's something. It's not interesting. The only problem is that you cannot tell which 1% is useful. Imagine this topic 100 years ago. Good afternoon. Thermal radiation, the black body, and so what is it? Why is this useful? Why is this useful? You will see it's very, very important because to explain this, you have to leave the classic approach of physics, mechanics, thermodynamics, and you have to understand the quantum mechanics, the microscopic, so the dual nature of particles and some special behavior of very small particles. Doesn't matter. Let's start. All body which has temperature which is higher than absolute zero, it is mostly most of the body, all of them actually, has a radiation. This radiation is electromagnetic radiation. This is come from the heat and lot of other things, and it has a peak, and you can do a spectra. I will show a spectra, the intensity and also the wavelength or frequency. For example, you can go to a workshop and buy a light bulb. Nowadays, there is something written, the color temperature. That's it we are talking about. The black body radiation, actually, of bulbs and everything. I'm talking about not the this diodic stuff, but I'm talking the old one and the halogen stuff. Because, and not these lights, the light bulb, the old one. The universe has a temperature. The universe started, I don't know now when, because the standard is changing, 15 billion years ago. Then it was like a point and expanded. It was full of radiation. First, the particles and the photons had collision, but once it became transparent. And since then, it expands. So, this temperature is something 2.5 Kelvin, and it is visible in radio frequencies. If you want to measure the temperature of the sun or the stars, then also you have to determine the spectra, the full spectra, And then you can determine the temperature. There are some other things like you will learn about it. Actually, you have learned because this spectra has some cavities, gaps, and everything. These are the not emission. So these are special frequencies of hydrogen and other atoms. Actually, this comment is bad. The sun and stars. Do you know? Can you tell me which is the nearest star? Who said it? You. Okay. Yes. Good. You are better than some so-called astrophysicists. They told me during my studies, I was astronomer, they were astrophysicists, the nearest star is the Proxima Centauri. No, the sun is. We can determine the temperature of the sun in this way. You will see. Okay. Spectral emissive power. Well, it's very simple. There is an energy, and this energy is depend on temperature, the wavelength, and also we do a normalization with the surface. I will explain you all this more later. Black body. The perfect black body, all body in the nature has some reflection. The moon, for example, is very bright, very nice. Its reflection is something, what is the name? It's, so its reflection is 3%. So the 3% of the sunlight is bounced back from the sun. This is the color of the dust or the ash. It's gray. So there are some experiments when they try to do black and more black and blacker bodies, but there is always a radiation. But we are working with a hypothetical black body which has no reflection. Every radiation is came from inside. But this is a useful thing if you want to determine the temperature of stars or temperature of, for example, not a star but something metal or something like this. There were some there are experiments, and they add some theory and try to fit something. The first thing was this Stefan Boltzmann radiation law. This is radiation of the absolute black body. Very great. The P is the heat power. A is the surface. T is the absolute temperature. So the Stefan Boltzmann radiation law fitted the theory for the measurements, and said, okay, the heat power is proportional to the fourth power of the temperature. Later it was add this surface and then a coefficient, the Stefan Boltzmann coefficient. So this is the value of this coefficient. Do you have a pointer? Might. Can you hear me? There? Okay, then I don't need it. So, this Stefan Boltzmann radiation law, a black body with surface area A emits per unit time a thermal power proportional to the 4th power of its absolute temperature. I will show you something very soon. Yes, this one. No, this is not that one. Okay, this was the first try. Next try. We have power, we have wavelength, and we have these curves. So these are the prediction of the next law, means displacement law, and it looks nice. If you see the colors and the temperature, the shining, so the radiation, it starts with red and then go until green, blue, and yellow. Actually, it's not expected, but the visible light starts at 800 nanometers. That's red. Then it goes until 400 nanometer. It's blue. And then there is the ultraviolet until 0.1 nanometer. That's the X-rays. And then I don't know what is the limit between X-rays and gamma photons. If you check the stars, you look at the stars, and actually you use you have to use a telescope. Some of them visibly red, some of them visibly blue. With naked eye, you cannot see this because the structure of the eye, on your retina, where your eyes detect the photons, the light, the color stuff is in the middle, and there are other receptors around it, which is for the light. And during the night, you actually see in grayscale, just your brain with colors. But if you have a possibility, a binocular telescope, collect more light, then you can see the stars are red or blue or something like this. The red stars are huge stars or sometimes small stars, red dwarfs, red giants. The temperature is lower than the blue stars. Our sun, for example, from the space, is white, with the color maxima at the green light. Just because you learned that previously, I hope, the scattering of the light is anti-proportional with the wavelength, actually the 4th power wavelength. From the white light, the blue disappears, the dust filters the red, and you can see something yellow, but it's not really important right now. This is important. They, actually not they, he, started to determine this black body power spectra, and what he find is that the wavelength and the temperature are anti-proportional, and introduced this constant, this Wien constant. This is the displacement law, or the Wien's displacement law. That's great. And this is good for short wavelengths. Short wavelengths means for blue light, and low temperatures. There were other try. They tried this railing and genes tried to fit for the experiments and other formula this energy as the function of frequency and temperature. C is the speed of light. Of course, everything in SI. The K is the Boltzmann constant. You can change the frequency for wavelength, and that's still very weird because usually I use circle frequency, omega, not this one. But you can see this energy is the anti-proportional with the fourth power of the wavelength. This is the statement. Very nice. And here, the Hungarian is a very difficult language. It is written kísérleti spectrum, but you have to pronounce it experimental spectrum. And there is written in formula, and it's formula, so it's understandable. Sorry for this plot. I did it last night, and I just copied somewhere this one. So the black curve is the experimental spectrum. So there is a black body, a given temperature, and then I measure the radiation at radio waves, at infrared, visible light in different channels. You know what I'm talking about. You know electromagnetic radiation, don't you? You know it's well, okay. Sorry, it seems your abilities is much better than I have ever heard. So thank you for coming to my lecture. It's really an honor. So the black is the experimental spectra. I have given you this Wien displacement law, and that is there. Actually, the fitting is not so bad. So if you look for plots on the internet, it's not so bad. And there is this this other formula, and this formula gives this one. And this is good for higher frequencies. Lower frequencies. No, doesn't matter. There is something that's called ultraviolet catastrophe. It means if you decrease the wavelength, then this law, this formula, gives infinity for the energy density. That's not acceptable. This is not in the experiment. So something is bad, very bad. Such an interesting thing, not so important, radiation of black body. It's 100 years ago, they could not explain properly based on that state of the science. Actually, there were also very interesting questions. For example, if you ask like children, why is the glass is transparent and why isn't the metal transparent, then they could not explain this. It's not possible to explain. You need quantum mechanics to explain this. So let's go forward. Let's progress. They had some approaches. Yeah, so they have theory for one part of the spectrum, other part of the spectrum, but it was not satisfied, they were not satisfied. So they had an experiment, and it was evident that they needed some new approach. So with radical new mindset, Max Planck, a German scientist, developed a formula and later explained the formula. Both giving the formula, both giving the theoretical explanation is a great deal. Why? I am here. I can take the battery and I can rise. So it has more and more potential energy. Any potential energy I can set. That's nice. The radical new hypothesis is that it's not possible. All things are small oscillators, and these oscillators would have some energy. And then could be twice, 3 times, 4 times, and 100 times the energy, but between these steps there is nothing. This is not what you can see right now here. This is not the common experience. You can do anything, so you can set all energies, but not in the microcosmos, in the world of particles. So the idea was that this is there is an oscillator, and the oscillator can take only some limited amount of energy. So there are desks. You have seen this when the hydrogen atom was explained, if it was really explained. In chemistry, you saw it. I think you never heard about Balmer spectra and other things. No? I will, if I have time, I will return for this. Yeah, I told you this. So the idea was the following. These oscillators has this energy, and the energy is it depends from the what is the name? From the frequency. Usually I don't use this F. Usually I use mu, but doesn't matter. So it is F right now, and there is a constant. That's the Planck constant. Planck didn't call this Planck constant. We honor him to give this, and all energy buckets has a minimal energy, and this is the frequency multiplied by the Planck constant. Okay. This is a wrong translation, this quantum action, but I could not find it properly. Quantum hatás. It's something quantum influence or something like this, the right translation. So Planck introduced the following formula for the spectral density of this black body radiation. The frequency is there, it's cubic Also, there is dependency with from this temperature and also with the frequency. You can transform this from frequency to wavelength if you want. This is the formula. It's not so easy. Okay, it's not easy to memorize, not easy to calculate, but the result is much better. So the Wien formula, this law was not so bad. It was close, but it was not perfect. The Rayleigh's formula was not good, and no one mentioned the Boltzmann formula, but this is good. So this gives really the spectrum that we can see. It has horrible consequences. It means that the world is not that we thought what we can see. There are more. You have learned about special relativity? No? 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 No special relativity. Okay, I will ask. Because you should have learned about it. Doesn't matter. So the world is different than we thought. And because I still have 20 minutes, I cannot show you because I don't have internet. Later I will send you. Okay. There is something that called photoelectric effect. This thing was not known 1.5 centuries ago. Now the photocells, the CCD devices, or the old days the photometers, this night vision stuff based on this effect. What it does mean, if you have light, you radiate with light metal, then electrons leaves. There is a current, that means electrons, and the electrons. This was discovered by Hertz, and see this one. You know this experiment. This is there is vacuum in the sphere, also metal pieces, and if they are charged, then they form an angle, otherwise they just hang. This lamp, Eve lampa, it's something electric, based on electric belt, actually, and it has blue or red or white light, strong. This disc is zinc, and this light charges this disc, this metal, and you can see. So this is this Hallwach-Ströer effect. And there are some interesting things. This works in ultraviolet. It do not work in red or infrared radiation, just ultraviolet. That's very rare. Yes, this is something similar. Sorry for this slide, it's Hungarian. I will translate for you. We know Einstein from this special and general relativity theory. I hope you have seen the interstellar, for example. That's a good demonstration of general relativity. But The general relativity theory was made in 1920. The special relativity was made in this time, but the Nobel Prize was given Albert Einstein because he explained the photoelectric effect. I don't know whether is it true, the committee gave the Nobel Prize for this, for him, but they tried not to consider this stupid publication about the time dilatation and other things. The special relativity was made with the help of his wife. She was Serbian, and also with the help of Minkowski and other Lorentz and other physicists. The special relativity is not only Einstein's creation. So we have metal. In the metal, perhaps you know from chemistry, there are ions, and there is a electron cloud, a common electron field. So the electrons can move freely. The effect is very weird. A photon comes. The photon is the particle of the light. What I told you, I just told you, the particle of the light. Wait, because you have optics, and you have refraction. You know the light. You know rainbow. You know that the light has wave features. Very well. There was a big argument between Newton, who invented the geometrical optic, and also this wave features of the light. But I told you now the photon is a particle of the light. Actually, it is my imagination is a short piece of wave, and so the light comes and hits an electron. The electron got energy, and the electrons are moving inside the metal because they are bounced. But it has actually a potential, but doesn't matter. So the electron got energy from the photon, and then tick, it could leave the metal if it's enough close to the surface. The energy will be something kinetic. There is something which is necessary work for leaving the metal, and there is a difference. This h times multiplied f. H is the Planck constant, and the f is the frequency, which is given by the photon. This is understandable only then if you accept that the light, which is considered a wave, is particle. This was the explanation. It was published by Albert Einstein. I said Einstein because I'm Hungarian, but Einstein, if I know well. And there is no Einstein, anything doesn't matter. So this wove a Nobel Prize. Okay, this is common. We use this. This is how we can, you electrical engineers, all of you, we can deal the light. We have light, and then we have some current, and then we can do something. So this is the way, say, in a different galaxy. Let's explain this. The The first experiment is that there is here, I think it is visible. This is vacuum. This is so-called anode. This is the cathode. There is some tension, electric voltage on this. And the light comes and hits the cathode. And from the cathode, it hits electrons. They move this way and gives a current. And the intensity of this, the magnitude of this current is proportional to the intensity of the light. This is an important feature. It could be something else. It could be cubic, it could be fourth power, or it could be anti-proportional, whatever you want. The next one, this is more different stuff. It says there is a minimum frequency, a minimum energy that is necessary to hit the electrons from the metal. So there is a threshold, a minimum energy, and you need this to hit electrons out from the metal. And also, if you have this, then the current, the number of electrons, are proportional with the intensity of the light. Okay. I just told you this. Great. Okay, some stuff that what I haven't mentioned is that the reaction is immediately. So the light comes, the electron leaves. So it immediately happens. Also, which is important, that I have told you the energy of the photon is proportional to the frequency of the photons, the electromagnetic radiation. Okay, sorry again. In English, it's not understandable because we called in Hungary Röntgen examination the X-ray examination. Röntgen also got Nobel Prize for discovering the X-rays. What they are? There is a glass. In the glass, there is a vacuum. There is a cathode. It's minus charge. Anode, it's plus. And if you accelerate electrons with it, and it hits the anode, then you will experience X-rays. Okay, this happens sometimes when you don't want to do it. In radar stations, you also had this. There was an accident when some guys in the hot, actually it doesn't matter, it was not hot, just made some work in the radar station, and there were these special equipments radiating the radio waves, and there were concrete at 1 meter. And after the work, everyone was red above 1 meter, because the radar, which should be emitted only radar radio waves, emitted also X-rays. That was a very, very interesting thing. This Röntgen or radar or X-rays, so they are just electromagnetic waves, that their energy is very, very high. It could pass the flesh, the walls, and everything. In the first time, they didn't know that they can destroy the DNA. They didn't know what is DNA. Just they didn't know what is radioactivity, and they didn't know it can destroy the cells in a body. So they used large doses, but we still use this one actually. There are other ways for this. There are, if you want to check something, you can, instead of X-rays, you can use mesons. That's a special type of electron-like particles. You also can use ultrasounds. Doesn't matter. It's not important. Which is important? These X-ray radiation. It has waves, and also it has particles. And there is a special way of examination when you use X-rays, and these X-rays do not just pass the material, but they could scatter on atoms. I will show you something similar, and you can do it. For example, neutrons. Neutron is a particle, and not only the photon has particle and wave dual nature, but all particles. Even you, just your wavelength is too small, so macroscopically you cannot see the atoms. You cannot measure. But with neutrons, protons, hydrogen atoms, hydrogen molecules, they have done this double slot experiment that you have seen previously, I guess, because I saw in your notes. Yes. And now that's something important. Quantum scattering. This stuff is very, very important. Quantum scattering. Sorry for the Hungarian text. What does it mean? You have a Röntgen source. You have something, a target. It's written here paraffin. Paraffin is something carbon hydrogen, and which is important is the hydrogen. It has some reason. For example, we can calculate the hydrogen atoms, and we can understand the hydrogen atoms. Understanding the helium atoms is much more difficult, and I had to write a midterm test from beryllium atom, and I had to calculate as physicist the beryllium atom's electron structure with 4 electrons. Doesn't matter, you will not have this midterm stuff, but we have hydrogen. In the hydrogen, the electron is bound to the core. It's a proton. It's quite simple. Actually, it's more difficult. Doesn't matter. The X-ray photon comes, hits the electron, and then the electron leaves. Also, the X-ray photon leaves, but its energy will be much lower, and the direction will be changed. That's a quantum scattering. Actually, scatter. It's not a direct collision. So you leave the photons, the X-ray photons, many of them, and some of them will hit an electron in a hydrogen atom in the paraffin, in this material. Which is important is this theta angle, and you can determine where is the maxima of this X-ray examination after the X-ray photons pass the target. It's statistical stuff. What you can see is that the change of the wavelength, because the energy of the X-ray photons changes, it means its frequency or wavelength also changes. Has this formula, and this theta, which is written there by nu, doesn't matter. It's not my plot actually, so it was given to me. Is this one. In practice, you will calculate this, and actually it's not so difficult. Why is this important? Why is this important? Because this is the proof of that the X-ray radiation is corpuscular. It consists of particles, photons. They, in that time, believe it's a wave. It's not a wave, it's a particle. Actually, it was not a good sentence, because it is both particle and wave. In the physicist has a song or poems that hogy is volt? Nem tudom, érek-e, vagy ez a hullám, mindegy, majd megtalálom a fizikusikat. Doesn't matter. So it's I'm so happy. No? I understand why I need this. Oops. Úgy látom. Úgy vagyok. Advanced technology. Okay. It works. I survived. Great. So this is one proof of that the light, the electromagnetic radiation, has particles. Do you deduct stuff? How often do you deduct stuff? Because I saw only some hints how to do, for example, how to calculate this Compton formula. You don't deduct? I will show you. I will not need my video camera, and I will show you. We can discuss this. Wait, I have 1 minute. Great. So the Compton formula you can calculate if you want. Great. I have still 1 minute, and this is the last page. The electromagnetic radiation has particle nature. It comes from the thermal radiation, the photoelectric effect, and the Compton effect. But also it shows interference, diffraction, refraction. So they are both. It's a dual nature, and the electromagnetic radiation shows wave and particle features. This is the end. My comment, all particles has this feature. That's quantum mechanics actually. So this is the end of this lecture. Thank you very much. If you have any question, you can take it. Thank you. And you can write me, and we will continue 10 minutes later, if I know well. Okay, great. Thank you very much. Pillanatban várjon, leállítom.